first figure is Yuki Arakawa. The title of his talk is two-dimensional topological quantum field theory associated with the vertex algebras.
So my great honor to give a talk on this specialization. The organizers here is the graph of my talk. So I start with Noah Arakawa conjecture on syncretic varieties. So this is a certain conjecture of the existence of two-dimensional quantum topological quantum field theory associated with syncretic varieties. So because it's QFT, we consider the category of so objects here compact oriented in one manifold, which means just the disjoint union. Of this line. It's just union, disjoint union of circles. Anamorphism of this category so often describe form between one manifolds. So this is compact oriented two manifolds. Sigma such that the boundary is V1 lines. So the morphism looks like this. So this is V1. And there's by joining the boundaries, there's an obvious composition of the morphism. And then, in particular, identity morphism between this one is just seen. So this is a usual category of the this is a monoidal category. So the tensor product is just a disjoint union. And we consider another category. Yes. So this is a category of syncretic varieties. But objects are not syncretic varieties. Objects are complex, semi-simple, algebraic groups. But the morphism between two groups are given by a certain syncretic varieties. So the form from G1 to G2 is given by syncretic varieties, which which might be a singular, equipped with the action of G1 and G2 and G star, such that G1 and G2, the action of G1 and G2 are Hamiltonian. And also the action of C star to the simple form, omega, is just multiplication. So I have to describe the morphism and composition of two morphisms, which is two symplectic varieties. So what is composition of home G1 and G2 and home G2 and G3? So elements here are certain symplectic varieties with two commuting Hamiltonian action G1 and G2. And here this Hamiltonian action G and G3. So the composition of X and Y is given by the symplectic reduction of X times Y with respect to the diagonal action of X. This is a symplectic reduction. So this is more precisely, this is set xy such that mu x y equals to mu y y. So this is corresponding a moment map of x and y respectively, and you quotient out by the action of g, diagonal action of g. This is, so because it's a symplectic reduction, you get a symplectic variant. Now, so what is the identity morphism from G and G to G? This is not difficult to see. It's a cotangent band with G, which is just G times G star. Because so there's a natural action of two commuting action of G. And so if you consider the symplectic reduction of this variety, this is just G times G star and X quotient by the action of G. But the momentum up here is just a projection to the second component. So because so this is G X Y is so this becomes mu X Y, something like this. So X, because X is completely determined by Y, so this is just G times X over G, so this is asymptotic. So this shows that the cotangent bound with 2 is identical. the conjecture states before. So this is again monoidal property. With the tensor product, it is just product. And the conjecture of Moore and Arakawa states that if you fix G, so you fix some simple group G, and then you fix a monoidal function from B2 to this category of syncretic varieties, which is a monoidal category, a monoidal functor, such that the S1 goes to this group G, so object. This is the corresponds to the object. And the morphism corresponds to identity. Morphism must go to the identity morphism, so it goes to here. Also, another property is that the cut goes to the G times so-called a constant slice, where S equals to constant slice, which is E times GF, which sits in the G. So here E, I fix SH triple such that E is regular. So regular of Principal. Then, so this is the centralizer of F inside G. And so this has a structure of syncretic variety because it's isomorphic to this twisted cotangent bundle. So it's another kind of twisted cotangent bundle, so it has a structure. So this is a conjecture which is still open.
How do they arrive at this? How do they arrive at this?
I explain in the third section. I will not explain, but I explain where it comes.
What's the connection of this one with the single module function?
So
What is this connection with the single Graham sequence module function or this
modular functor.
yeah.
Maybe it's not directly connected, but if I explain later. Now, so as I said, this is still open, but it's Moore and Arakawa themselves has checked for the validity of the conjecture for A1 and A2. So let me explain how it looks. So in the case of A1, the syncretic variety corresponding to pounds. So I should say, because there are lots of symmetry in the category to Buddhism, it's enough to define this syncretic variety and check a certain compatibility. So if you can define this syncretic variety, you are done. Now in this case, it's quite simple. You just tensor product of C2. And so because there's a natural action of SF2 on C2, there's three commuting action on the sheets corresponding to this one. And this has another structure also. And so again, this is still A1. If you consider symplectic variety corresponding to this one, this is quite already complicated. This is actually a minimally important closure in D. So this one is orbit of some root vector, and this is the singular variety. And because D4, if you write the extended affine Deakin diagram of D4, this is like this, so there's 4 commuting actions. So for A2, so what is the symplectic variety corresponding to counts? This is the minimum impotent closure in E6. Because if you write a affine Deakin diagram corresponding to E6, you have 3 commuting actions out of S3. But other separate varieties are mostly unknown. So we don't know what they are. So now I move on to the Vertex algebra side. So I explain a Vertex as an analog of more arbitrary conjecture. So I sometimes identify G with the algebra of G. And so if you do the simple, you define corresponding affine Tatsumori algebra. With visual commutation relation. And then you can consider corresponding affine vertex algebra. Here, I will show this university one was up here. So you can consider the corresponding affine vertex algebra, which is just as a J-hat model, it's an induced model from induced representation of this parabolic suburb. So here, GT is 0, and the chaos is this fixed value. It was shown by Haishan Li that the module of this vertex algebra is nothing but a smooth G-hat motion at level K. So you can think this as enveloping algebra. I can define the category of vertexes. But again, the objects is not vertexes. So objects are the same as before. So it's a complex simple algebraic groups. But the morphisms are given by vertexes, satisfying certain morphisms. The morphism describe form from G1 and G2. So I said that Gi and the E algebra of right. So this is this consists of conformal vertex algebra. So I say conformal vertex algebra instead of VOA because it may not be G graded and it may not be G, but half graded by half English. So this should have a vertex algebra homomorphism from tensor product of these two affine vertex algebra are the critical rate. So HI, so in the case of, if GI is simple, so HI check is just a Joule-Boxer number. Joule-Boxer number of GI. But if it's not a simple, you just consider tensor product of the corresponding singletons. And the condition is that this vertex algebra is integral over G1 positive part of F1 to these two subalgebras. Which means there's an action of group GIT. Now then I have to describe the conclusion of this category of morphism. So I take two vertex algebra from G1 and G2. We have V1 and G2 G1 V2. So you have two commuting Nash caption with G1 hat has a critical level and G2 hat has a critical level. And the G2 hat and G3 hat. And then, so if you consider tensor product of two this vertex algebras, there's a diagonal action curve at level minus h2 check minus h2 check equals to minus 2 times h2 check. And at this level, we can do the following reduction of the motions. And so the composition is given by semi-infinite cohomology, a relative semi-infinite cohomology of William tensor groups, which is a vertex analog of syncretic. So this is a relative semi-infinite cohomology. And so this is again monoidal category where the tensor product is just a tensor, usual tensor. Now the conjecture of Arakawa states that if we fix G again, there exists a monoidal functor of the category of two vortism to the category of this vertex algebra. And such that the vertex, so S1 should go to that fine vertex algebra corresponding. No, it's just a G. So objects, S1 should go to this G, and the condition is that the associated variety of the image of the morphism should equal to the syncretic variety which conjecturally exists by Moore Tachiko, where